Welcome back, everybody. So we were in the middle of looking at the logical level of wide column stores. We looked at the model with columns, column families, rows, row IDs. We looked at how to query them with get, with put, with delete, with scan. So again, I repeat, this is all low level, right? But we will keep adding stuff on a higher level, right? So the idea is a separation of concerns, right? You first focus on the implementation of the whole architecture using just bytes, and then you can add the layers on top. All right, so now you know what the key value model means. It's everywhere. You know what column-oriented storage is, that even exists on a single machine, right? This is really just about the way you store it on the hard drive. And wide column stores, now this is for clusters of machines like the ones we have. There are actually plenty of implementations out there. Google's Bigtable is the first one. HBase is the open source thereof, and Cassandra is another one. And now there's probably more out there. There are even some of them that are even larger. I will come back to it probably tomorrow. All right. Is everybody ready for the physical layer? This is the most complicated lecture of the whole semester. If you survive this, you survive the course. Right? I'm just warning you. So I will take it step by step. We'll take the time. I can repeat, take the time to answer questions, come back on some of it tomorrow if necessary. All right, so fasten your seatbelts. So the first thing, now we are looking at the physical level. What is the first thing that we did when we put files in HDFS? We cut them into chunks, right? So there's the idea of partitioning the data to make it fit and spread it over clusters. We have exactly the same idea of partitioning the data. The most natural way to partition the data would be on the rows or on the columns. Who thinks it's on the row that is the most natural? Okay. Who thinks it's on the columns? Okay. Who thinks it's on both? Aha, yes, it is indeed on both. Because on the rows, remember that the row IDs are sorted, right, by increasing value, so that we can define intervals. So every interval is basically made of a row ID and a row ID. Now, the convention, because it's actually very convenient and beautiful, is to have a mean inclusive. So this is really the first one that is in this interval, in this region, and the maximum exclusive, meaning that it's not the last one, but it's the one after that, right? Why? Because then the maximum exclusive is the same as the mean inclusive of the next one, right? So this is the main idea. So this is called a region, right? So this is the horizontal partitioning of the table in regions. You can have a lot of regions. You can have thousands of regions, even more than that. Okay. And we can also partition by column families. So indeed, we do the both of them. So a partition is basically like this. It's actually like a wedding cake, right? So you basically cut it both horizontally and vertically, and this is stored together. This is something that we call a store, actually, what we put in there, but I'll come back to that. So the intersection of a region, which is an interval of row IDs, and of a column family is a store. Now we are going to be doing something that actually we've already done plenty of times, and I keep repeating it over and over and over again. Who knows the reference, Dinner for One? Okay, if you don't, then watch Dinner for One on New Year's Eve. Anyway, so you know that we have a centralized architecture with a name node and plenty of data nodes. I told you, be careful. The name node and the data nodes are actually not machines. They are processes running on the machines. And that means we can have multiple processes. And we actually are going to have more processes. Now we are going to have a process called HMaster that is running on the coordinators node. And we're going to have region servers that are running on the same machines as the data nodes, right? So it's very common. Do we have a question? I saw raised hands. So we have the region server processes on exactly the same machines as the data nodes. You will soon understand why. And typically the HMaster runs on the same as the name node. Now I can say quickly, because since we already covered this with HDFS, just like in HDFS, we have standby and observer name nodes, we also have backup HMasters. You can have up to 9 backup HMasters, making it 10 in total, and they can take over. So we have the same kind of redundancy to address the single point of failure. All right. And so now I'm going to first go and describe the HMaster, and then we'll go to the description of the region servers, right? So one by one. So that shouldn't surprise you. Just like the name node is responsible for the metadata operations in HDFS, the HMaster is responsible for the metadata operations in HBase. In particular, if you want to create a table or delete a table, that all goes through the HMaster, right? To do these sort of things. Also creating column families, removing column families, all these things have to go through the HMaster. DDL means data definition language, right? As opposed to DML, data manipulation language. So DDL is the high level, and DML is when you actually query or update the data. Okay. Now, the distribution of the data over the cluster is actually done based on the regions. This is why they're called region servers, in fact. So it's done based on the regions. So it means that what happens when you create a big table is that it's going to partition this space in regions, and then the regions are going to be assigned to the region server. So here I put 4 region servers as an example, and every region server is assigned multiple regions. Now, my slide, I just put 2 of them. In practice, that can easily be 1,000 regions on each server, right? Just like you can have thousands of blocks on the same data node in HDFS. So we can have easily 1,000 regions assigned to the same region server, okay? Now, what happens is that unlike HDFS, where we can only append at the end of a file, in HBase, we can actually add rows anywhere we want, even in the middle, completely in the middle. It doesn't have to be at the end. So what happens is that you could have at some point some of the regions that grow because it's based on an interval, right? So if at some point you add a lot of row IDs inside the same interval, that region is going to be very, very, very large at some point, all right? And so what happens is that when it's too large, something is going to be done actually locally by the region server. So for example, this region server here might have noticed that this region here has become too big. It might have, for example, 4 rows, but it has very large objects in there or whatever. So it's basically exceeding a certain size. So there is a whole process that splits the region into 2. Very carefully designed in multiple steps to make sure that nothing breaks. But basically it cuts the region in 2, and now it's 2 regions. So initially these 2 regions, they stay on the same region server. So they stay assigned to the same region server. It's just that now it has 3 regions instead of 2. However, at some point, you might have some rebalancing in the sense that the HMaster might notice, okay, there are too many regions for that machine. Let me redirect that region over here to this other machine, right? Some of it might remind you a bit of HDFS, because in HDFS2, the name node is able to say, okay, there are not enough copies of that block. Please, this data node should store 1 more copy of that block, right? So you can also do these sort of things with the blocks on HDFS with the regions here. But there are a few differences, and so I will try to give you the mental picture. First, the regions are assigned to the region servers. I didn't say the regions are stored on the region servers. They are assigned to the region servers. It's only a responsibility. It's a hat. So basically, the region server right there is wearing 2 hats, the yellow and the dark blue hat, saying I'm responsible for these 2 regions. It's only a responsibility. And actually, switching responsibility is very easy. You just say, okay, now the responsibility for the yellow region is no longer the 3rd one, it's the 4th region server. It's only an assignment, it's only a responsibility. Why am I saying that? Because where do you think the data is actually stored? Yes? Exactly. Yeah, in HDFS. It is stored in HDFS. So the data is in blocks, in HDFS blocks, handled by the data nodes that run on the same machines, right? But the regions are only assigned as a responsibility. Now, let me explain what happens when there is this change here. What happens is that this is a region, this one is responsible, and that region is stored somewhere. I will explain how in a moment, but basically it's stored on HDFS as files on HDFS that themselves have blocks. The blocks, by the way, many of them might be here. If it's been there for a long time, many of the blocks might be here. But you know that in HDFS, the blocks can also be spread, right? So maybe some of the blocks for the yellow regions might sit here or here. And because of the replicas, they will even be stored 3 times, right? So the blocks might be here, here, a little bit everywhere. So do you see that if I switch the responsibility of the yellow region from here to here, the blocks don't move. They stay where they are. Right? They're on HDFS. Everybody can see HDFS. So if this could see HDFS, this one also sees HDFS, right? The only thing that might happen is that if this region server has been responsible for a very long time for this block, it might have a lot of copies of the first replicas of the blocks in here. And when you suddenly hand over, then maybe at first, this one is going to have to read remotely over the network from here. That might happen. And then after a while, it will be localized here. We will see why. For whom does that make sense? All right. Do we have a question?
What does it mean to be responsible then for a region in the practical sense?
Be responsible for a region basically means that when a client wants to use HBase, I will come back later to it, but they basically request who is the server responsible for that region or for this. I'm interested in a specific row ID. Who is responsible for it? And there is a central place where you are told, okay, this server is responsible for that region. And then the clients, once they know that the yellow region is handled by this one, the client has to connect here. What happens is that the client could also attempt to connect here because it might think that this is still this one who is responsible for the region, right? So the client could connect here. But in that case, this server is going to answer, sorry, not my domain of responsibility. Just like in real life, right? You ask a work colleague to do something and they say, no, no, that's not my responsibility. It's the same thing. It's really that, right? Does it make sense?
So then the data is retrieved from the HDFS system and with the same process that we saw last week.
Yes, it's on HDFS, exactly what we saw last week and the week before that. Right? Okay. It is in HDFS. It's all files on HDFS stored in blocks on the data nodes. And as you know, anybody can log into HDFS and see the files. So what is very important to understand is that all of these machines, in spite of being responsible for specific regions, every machine can see all the data. Right? The only reason they would deny a request is just if they are not being put in responsibility of it, but they can all see all the data through HDFS. Right? Any other questions? Yeah, over there.
Excuse me, can you just repeat what happens when a region server was responsible for a long time for a region and what the link with the cookies fast for me?
So basically, I will explain to you in the rest of the hour and tomorrow what actually happens, the way that it's stored in HDFS. I will tell you all of the details of that, what the files look like and how they are written and so on. But basically, now you just need to trust me for now, but in an hour or tomorrow, you will understand why I'm saying that. Because of the way that the files are written, if a region server is responsible for a very, very long time for the same region and it's not moved to somewhere else, this server is going to write a lot to HDFS data from that region because it's responsible for it. Do you remember that in HDFS, I told you that when an HDFS client connects to HDFS and creates blocks, where is the first replica stored? On the same machine. Who is the HDFS client? The region server. So it requires a bit of mental gymnastics because you have both HDFS and HBase. But basically, this region server here is in particular an HDFS client. Like anybody else, it can write to HDFS. And as an HDFS client, it might write block to HDFS. And because it turns out to already be on a machine, then every block will have a copy on that same, on the data node that runs on the same machine. That is the reason why, if you stay responsible for a region for a very, very long time, you will tend to have a copy of most of the data you're creating, plus it's replicated at other places, right? But of course, if you start creating so much data that it doesn't even fit anymore, then the blocks are going to go away and spread all over the cluster, and then it's going to be slower, right? Did I answer your question? Yeah. And a lot of that will become clearer once I have explained what happens with the files, because I still have to explain that to you. All right? So again, I repeat the most important. We have two layers here, HBase and HDFS. Now, 2 weeks ago, I told you about the logical level of HDFS and the physical level was the hard drives on the clusters. But now we're one step above. Now the logical layer is HBase and HDFS now is a physical layer, right? So you really need to think in this modular way in terms of all of these layers that are on top of each other. And so it means that HBase is a user of HDFS, right? HBase uses HDFS as the storage medium for all the data for the tables. Okay? And this is why each region server is also an HDFS client and will read and write data to HDFS. Now, who is in charge of managing all of that data stored in HDFS? It's HDFS, right? So it's the name nodes and the data nodes that are going to handle all of the file namespace and the blocks and so on. We have a question over here.
For the, is the HMaster and the name node, is this the same thing or is this like two separate?
So these are two processes that are running on the same machine.
Ah, okay.
Yep. You don't have to, but usually this is what people do. They basically install the data nodes on the same machines as the region servers and the HMasters on the same machines as the name nodes. Now, in practice, I think that the backup HMasters, you could also put them on the region servers. So you would basically have the main HMaster here, and maybe this region server could also have a process that is a backup HMaster that could take over, right? So you have flexibility because you can run any number of processes on the same machines, right? And then it's just best practice to do it this way. Did it answer your question? Yeah. All right. We have another question over here.
So I'm thinking about a common SQL use case, and it like one thing I would anticipate doing is pulling up a row or a given set of rows and having a bunch of different fields. And in this situation, it seems like for any given record that a bunch of the different information for those fields might be distributed across a bunch of different places. And so then is the paradigm that this kind of computation in which you're operating on multiple fields within a record all at once is discouraged, so you can try and make these operations independent of each other so they can be distributed? Or do we kind of accept a certain degree of latency when doing that full record access?
So that kind of patterns is absolutely encouraged. You're encouraged to do that, but it might sound like magic, right? I'm telling you, you can actually have random access all over the place in the table and so on, and it's running on top of HDFS that has high latency, right? So it might be a mystery, but I will explain that. It's the magic of the technology that we manage that. But basically, the answer is definitely yes. These patterns are encouraged. You can read anywhere you want in the table, and that actually is going to work, and it's going to be very, very efficient, right? But I have to tell you how. I will basically give you all the details of that.
Thanks.
Right? Okay. You have the right thinking, exactly the right questions. Okay. Now, since I've explained that to you, can anybody tell me why we don't assign every region to 3 region servers to avoid data loss? Yes? Exactly. HDFS takes care of that. HDFS already duplicates the blocks, at least in 3, can change it. So there's no point in replicating the regions, right? Because the data is already redundant. If a server crashes, imagine that, let's say this one crashes, that's okay. You just assign the responsibilities to somebody else. You don't lose any data because HDFS had already been redundantly storing it. Yeah, so that's exactly it. Okay, perfect answer. All right, just checking for raised hands. Is there a raised hand? Yes, over there.
if the HMaster lets the HDFS system handle all the redundancies, how does it know which region server to assign the new responsibility to not assign it to something that doesn't actually have a single copy, for example, in the worst case?
So two things. First, there is a place, it's called the meta table. I'll come back to that. One of these, where is it? Here. One of these machines has a small table, just a few megabytes, fits on one of the machines, let's say this one. That's called the meta table. That meta table is a catalog of all the regions and all the machines that are in charge of the regions. And it's kept up to date the whole time. So whenever there is a change, they will communicate with that one, and the table is kept up to date with the instructions. Now, imagine you change the responsibility of a region because a server crashed, for example, and you want to assign it to somebody else. So the first thing that I want to say is, you could technically, if you forget about performance, you could assign the region to absolutely any region server. They all have access to HDFS, they all see all of the data. However, you need to be careful because some of them, as you correctly said, might not have any local copy of the block. So it means that if they want to see the data, they will have to connect to other machines, and it's going to be slower. So you absolutely have a point. And it is absolutely true that ideally, if you have a way to know if there is if a lot of the blocks tend to be at the same place, then you will pick a region server that already has many blocks. The problem is that it's not so easy, because you might remember that the first replica is on the client. So when you have been for a very long time responsible for the region, you have a local copy. But now you will not really have any other machine that would have a high concentration of the blocks, right? Because by design, we spread the blocks all over, right? But that's not a problem at all, because what's going to happen is that at first, when the region server starts being in charge of that region, it might be a bit slower. But over time, as it takes responsibility for the data, somehow the data will come back with a local copy on that machine. It's just like the collapse of the wave function in quantum physics. The same thing is happening. Like at some point, all of the blocks tend to come back to the region server over time, right? Okay, and it goes both ways actually, because also as you have many blocks, they might start spreading all over again. But this is all orthogonal to the system because everybody can see everything. Does it make sense? Okay. Yes, we have another over here.
Is there maybe a point in the fact that the data is completely always like in the HDFS, data is completely written like from the end to end, and like in this case when the like just like that point which you said now, like the last one, does it have connection that data is always like completely written, and then like that's how the data comes back to this data node which was assigned to? Because if you like kill previous copy and now the client again connects, yes, then the data comes now to the
that is exactly what happens. So basically the reason why the blocks tend to come back is that when users use HBase, they are going to modify the data, to update the values, to add values and so on. And we will see when I come to that what the region server is going to do is going to get rid of files and recreate new files. So the old files are the ones that were on other machines, and that it will delete. And the new files that it's going to create will have a local copy on the same machine. That's the reason, right? This is really because of the turnover. You keep replacing and rewriting new files and deleting the old ones. Yeah. Does it make sense? Yeah. Okay. All right. Yes. Another question right there.
Thank you. How does HMaster know if, for example, region server crashes? How do they communicate?
So it's the same sort of protocol as we have in HDFS. There is a way to keep track. So in HDFS, we use heartbeats. that allow you to keep track of the available processes. And so there is something similar in HBase that allows the HMaster to know which region servers are available and which ones are not available. It might not be exactly the same as Heartbeats in HDFS, but there is something similar that basically allows it to take care of that. Right?
Thank you.
All right.
There's one question on Zoom that is
Yes,
almost the
let's go.
same question, I think.
Uh-huh.
Does the communication between HMaster and the region server also rely on heartbeats, just like HDFS?
So that I don't have the details of, but that's a good homework. Maybe we can work on that and try to find out the details of the communication, right? That's a good point. Shall we continue? Okay. So I didn't scare you so much just yet. Okay, so now we've discussed the difference between the HBase layer with the region servers and the HDFS layer with the files. We've discussed what happens if there's a crash, that you redistribute the responsibilities. Let's go to the region servers now, which have the responsibility for serving the data to the clients. So I told you about this wedding cake that has both the horizontal and the vertical separation. Here, this is basically going to be served by the same region server. This might be another region server, but nevertheless, we also have this vertical partitioning. So this is now where I have to tell you why it also makes sense to partition vertically. Technically, every one of these intersections between a region and a column family is called a store. It's called a store. Now, if I look at one store, so it means that I'm looking at just one region. It's an interval of row IDs and just one column family, so the same color. Here I have these Indo-Arabic numerals. So look at the cells here. This here is one of these values, could be atomic, could be an XML file, a picture or whatever, up to 10 megabytes, or maybe even more, just would be slower. So this is called a cell. Now, what happens is that this is a logical view. It's purely logical. The table has rows and columns, that's logical. But how does it need to be stored in HDFS? The only thing that HDFS knows, just like any file system, is bits. We can just store bits, ones and zeros. So how can we turn that into bits? I will explain, but basically these bits are called H files. So the files that are created on top of HDFS, so HDFS files, are called H files. I will show you everything about what there is inside and how they are structured and so on, but this is called an H file. The same store, which is one region, one column family, might be over multiple files. I will also explain to you how this is done over multiple files and how it evolves over time. So basically, we store and persist the data in one of these stores over multiple H files on HDFS. And typically, after a long time, after writing them, you will have a local copy of almost all of the data locally on your machine. Now, let me dive a little bit into that, how this is done. So basically, what happens is that my H file is just a list of the cells. Remember, a cell is the intersection of a row ID and column. That's one value. So basically, my H file is just a list of them. So here, how many cells do I have? 6, right? 3 times 2. 1, 2, 3, 4, 5, 6. So I store a list. The red one, the purple one, oh, I didn't put the same. Oh, yeah, no, because it's ordered like this lexicographically. So A1, A2, B1, B2, C1, C2, right? So A1, A2, B1, B2, C1, C2. More exactly, what I store is the coordinates of the cell and the value of the cell, right? The coordinate of the cell is like playing Battleship, right? A1, A2, so this is basically the row ID and the column family and column name, right? So that is the key. And here is the value of the cell. Yet another key value model all over again. This is the key value model. The key is just the coordinates, the Battleship coordinates of my cell, and the value is the value of the cell. An H file is thus just a list of these key values. The key values in that context are very often written camel case, K-E-Y-V-A-L-U-E, with capital K and capital V very often. So basically, an H file is a list of key values where the key is the coordinates of the cell and the value is the content of the cell. That's what there is in an H file. Now, if you look even closer to the H file, what you will notice is that it's not just a value, a list of one value for each cell. It actually remembers the past. There is a whole versioning system that remembers past versions. So if you look at A1, then in that H file, you might even have former versions. So the latest version is version 4, but you will also find version 3, version 2, version 1. It will remember, just like GitHub. Okay, so this is a very nice feature. Another aspect of the way that this is handled is that when people want to modify or modify a value or add a value and so on, it's locked by row. You can never have two clients that are modifying the same row. If anybody wants to touch the same row, they have to wait and queue in line. So there is a lock on the row. And this is why when you have a lock like that, it allows you to have a total order. Version 1, then version 2, then version 3. This is to be contrasted with Dynamo. In DynamoDB, we did not have this. We could have inconsistencies, we could have conflicting values, and then we had a DAG of the versions, right? Like in Git, it's a DAG of versions. But here, it's not a DAG. It's really a line because it's a total order. And the total order is achieved with locking the row every time. You never have more than one person at a time that touches the row. Okay, so it's consistent. Does it make sense? Okay. All right, so now let's dive deeper because I told you we store the cells in the battleship way with a list of key values. More exactly, a file is a sequence of bits, right? So basically every key value is going to be a sequence of bits. And so in the H files, I just put the key values one after the other. And if I zoom in on this key value right here, it's made of bits and I can look now at what there is in there. So if I look at what there is in one key value, I will first have a key length, which is the length of the key, because it can vary, right? The key has the row ID, it has the column family, the column name. It's not a fixed size. So I store the length of the key here. I store the length of the value, which can be very small, but also be like 10 megabytes. So I need to store its length. And then I store the key, which has a variable length, and I store the value, which has a variable length, right? This doesn't vary. I think it's 32 bits and this is 32 bits. So that is already known. You know that this is 32 bits. But if you read this and you read that, you know exactly how many bits to read here and you know exactly how many bits to read there, right? So in spite of being variable, you know the boundaries of the keys and the values. It's important because you're looking at bits. If I just throw a million of bits at you, you will be unable to tell me where they start and where they stop, right? The only way to know is to store the length of the fields that you want to read. For whom does that make sense? Okay. This is actually known as a prefix code. Who was in information retrieval? Okay, so I open a parenthesis for those of you who are in information retrieval, you already know prefix code. That's the gamma code. The gamma code is a magic code that allows you to write sequences of integers of any size, one after the other, and you know exactly when they stop. It's magic. So for example, here, you know that this is 10. I will come to the question on Zoom. So basically, the way that the gamma codes work is that you count the number of ones until you reach a 0. So here there's just one of them, so you read one more bit. Then you cut here, you know that it stops here, and then you take that purple bit and add a 1 on top. So that's the number 2 in base 2. Next one, how many ones? 1, 2, 3, 4, 5, 6, 7, 8 ones, and then a 0. So now I count 1, 2, 3, 4, 5, 6, 7, 8, and I know I stop here, right? So now I can just take that over. I just need to always add back the 1 on top of it, but I take these bits, and this is the number. And I know that I need to stop here because of this sequence of ones that stops with a 0. Then again, 1, 1, 2 of them, so I read 2 more bits here, and that is 0, 1. I add back the 1 on top, that's the number 5, right? And then 1, 1, 1, 0, 1, 0, 1, one more number. This is called a prefix code. Just like the phone numbers, when you dial a phone number, it's a prefix code as well. It exactly knows when the phone number stops. It's magic. I mean, on a mobile phone, you no longer notice, but on a landline phone, you do notice that it starts dialing exactly after the right number of digits. Yes? Yeah, that's called the gamma code. It's more for those who had information retrieval to connect it. It's not important. It's not part of the material of the lecture. But let me give you the intuition. The idea of the gamma code is that when you start reading from left to right, at that point, you don't know the boundaries of the integers. It's just a bunch of zeros and ones. But the way that it works is that you start on the left. You consume ones until you reach a zero. So there is one, oh, then a zero, I stop. How many ones were there? Just one, so I take one more bit here and that stops here. Then I have zero, I always add back a one here, okay? Then I do the same here. I consume all the ones all the way to the first zero here, and then I count the number of ones that I had, and I consume as many bits right here, and again, add back a one on top. That is the gamma code. And I can go do it over and over and over and over and over again, right? Oh, it's you could also not add it, but you gain one bit. It's a compression thing. You basically gain space, so to say. It's an optimization. The idea is very simple. It doesn't work in base 10, but in base 2, except for 0, any number starts with a 1. You agree with that, right? Any number starts with a 1 in base 2. So what you do is you just remove it. It's implicit. Right? Does it make sense? Right? It's a very good question because that doesn't work in higher bases than 2. Yes? Not necessarily, because, oh, it just happens to be this here could be a 1. It could be a 1. Yeah. All right. So this is for those of you who had information retrieval. I just wanted to remind this. And for the others, don't worry, gamma codes are not part of the lecture. What I wanted to say is that these are the sort of tricks that tell you the boundaries of the regions of bits that you're reading, which brings us, I think, to the question on Zoom, which is the continuation of this.
There was one question, how do we know the length of the key length and the length of the value length? But you already mentioned that. That was also answered in the chat already. So it's fixed.
Do you know the Baron of Munchausen with the bootstrap? We call it bootstrap because he can just pull the straps and get in the air. So this is exactly what's happening here. We need to bootstrap it. It means that we don't know the length here, but here we know the length because it is always 32 bits. And here it is always 32 bits. So we bootstrapped it, and then we know the lengths that follow.
And the next question is, but if we want to read some key value in the middle of H file, then we still need to scan from the beginning?
Yes, absolutely. You need to be careful. You need to at least know when you start, because if you just land in the middle of things, then you don't know where you are. Yeah. Okay. All right, let's continue then. Oh, another question. Oh, that's okay. We just give the responsibility of the regions to somebody else. And there is no data loss because this is only one copy of the blocks and they are stored at other places. Does it make sense? Yep.
So this value can be, we said anything. It can be a table, it can be an
It's a sequence of bits. Yeah.
Is it possible to insert something in the middle of the value as a command, or do we have to like fetch the whole value, then edit it, and then get the whole value back to the server?
So typically we read that. Right? I will explain how we write that, but typically now we are reading, right? So it's already there, and we read the whole value. Right? Did you also have an injection attack in mind, or was it going in cybersecurity, or did you not go that far?
It was dependent on your answer, but I will wait until we get there.
Mm-hmm. All right, so I will explain how we write. The idea is that imagine it's already written. I'm explaining to you how to read it, right? Read the key length, the value length, and that tells you how many bits you read for the keys and the values. Okay. And then you can tell me if that will answer your question later. Okay. Let's now zoom in inside the key. So the key would be, that would be this here, this part here. Now I'm zooming in inside this. What will I find here? Well, you probably guessed it's the row ID, the column family, the column name, and so on. But we have to be careful because, again, we need to account for the variable length. So here's what you have here. Again, left to right. First, there is the row length. Again, that's a fixed number. We know how many bits to read. That tells us the length of the row ID, right? The row ID is here. I told you the row ID is a sequence of bits, variable. So this is variable, but the length is stored here. Then we have the length of the column family. That's also a fixed number of bits that encode that length. So we know how many bits we read. This is also variable, right? Then let me go from the right to explain this. I will come back to the colon qualifier. Here, this is just a deletion flag. It's a way to mark if a value was deleted or not deleted, right? So this is a fixed number of bits. And here, this is the timestamp. It's for versioning, version 1, version 2. That's also a fixed number of bits. Can anybody tell me why on Earth we do not have a colon qualifier length here, in spite of being variable? Yes? Exactly, we subtract. Because you remember here, we have the key length. Here, we have the key length. So if I know the total length plus the row length and the column family length and the fact that timestamp and key type are fixed, if I subtract, that gives me the length of the colon qualifier. Who is with me on that? Right? All right, excellent answer. All right, so this is how we manage to read the key and know exactly how to parse these things. Now you probably start understanding why you have to be careful to not have too long names for the rows and the columns, because they are in the key values. If you have very long names, you will have very long key values, and you have very long, billions of very long key values. So this is the reason why you need to be parsimonious with the length of the names. Any questions? Okay. Still have a few minutes. Oh yeah, on Zoom.
All cells in the store share the same family?
That is a very good question. I have also been wondering that if there's not a way to optimize and get rid, because indeed you're right. If you're looking at a specific store, it's the same column family for everybody. So why would you store it? I assume it probably makes things easier when you start moving data around and you basically look at the key values outside of a context, outside of knowing which store you are in. So it probably makes it a bit more resilient, that it carries over the exact context, right? But I've also been wondering if there's not a way to get rid of the column family, because that's redundant. Yeah. So that's half an answer, but I don't know if that was okay. Yeah. All right. All right. I will keep that for tomorrow, this one here. It's because I think we've already touched a lot today. So I will only ask you, probably need to refresh the page, how much you followed. I warned you it's the most difficult lecture of the whole semester, but we'll see how much damage I have done today, and if I need to repeat and accelerate, or on the contrary, if you've been following. Wow, this actually looks good. Very good. Yeah, slightly, of course, less than usual, but because I told you it's very difficult. But this is rather good. If you have, sorry,
Another question.
it is going to. Oh, we have 1 minute. Maybe we can go for that question.
Can columns in different families have the same qualifier?
Can two columns in different families have the same qualifier? Yes, absolutely. It's like two people having the same first name and different family names. Yeah. Okay, so thank you very much. If you have questions, prepare them for tomorrow. I will take the time to make sure you understand, then I'll take it from there. So enjoy your evening and see you tomorrow.